Hi everyone, in this section we will talk about gradient boosting. In the previous section we applied boosting by fitting our models on the residuals. This clearly only makes sense for regression problems. And the question is, how can we generalize these to different loss functions? Before we get to the answer, let's remember our mean squared error loss function. So this is our loss function for mean squared error. Here we will use a different notation, and we will show you that we can get the loss per data point, and we sum it over all the data points, then we can take the average and get the same result. And by following this notation, this is our loss per data point. So let's keep this in mind and go on. As the next step, we will look at the derivative of this loss function. We will take the derivative with respect to our prediction function f of x. So let's take the derivative together. Here's our loss function. So we will take the derivative of this with respect to f of x. In that calculation, we will take the power of 2, that will go to forward. This will be 2 over 2 and turn to 1. And this will reduce to power of 1 this time. And we have this minus sign here, that will go out. And overall, our derivative is minus sign, and then parenthesis yi minus f of xi. So we just calculated our gradient or the derivative here. So it's nice. Here I will point out something. If you remember, when I first introduced this loss function, I said that there is this 1 over 2 here for some reason. And actually, you just saw the reason. We use this to get rid of this power of 2 when we calculate the gradient. So it's all good. When we look closer here and rearrange the terms, we will see something interesting. When we look at the negative gradient, we see that that's equal to our residuals. So this is interesting. Because when we think of this in terms of some optimization techniques such as gradient descent, we will see some similarities here. When we apply this gradient descent algorithm, we take the derivative of our loss function, and the gradient coming out of that is useful to understand how to update our function so that we reduce our loss. We see something really similar here because this is telling us that my gradient is this much, and I should update my function with this so that I reduce my losses. So this totally makes sense to us. And how do we do this in this process? We fit those g sub k's on these residuals, and then we update our functions. So as you see, these are really similar processes. And this is going to tell us something, because this time we can replace this loss function with whatever loss function we'd like to use, as long as we can take this derivative. So let's put this into an algorithm. We can have this iterative procedure where we first take our model, f sub k. Then instead of calculating the real residuals, here we will calculate the pseudo residuals by taking this derivative. Then we will take our g sub k and we will fit that on these pseudo residuals. Then we will add that back to our initial function. And overall, we have a new model. Just like before, I will go back and compute the pseudo residuals, and be careful, not the real residuals, pseudo residuals. So we will take the derivative, then we will fit our g sub k on this, then again add back to this. As you see, this is just really similar. We only change how we calculate our residuals this time. And this is nothing more than applying gradient descent on the loss function, where we approximate the gradient using a weak learner. And over here, we can change the loss function to a different loss function, for example, log loss. As we mentioned before, the weakness of the learner is important because it works as a kind of a regularization in this problem. If our weak learners were strong, in this case, we would instantly overfit in a single learning step, and we don't like that. Also, the optimal step size needs to be decided. We usually do a line search first to find that optimal parameter, then we update the function like this. So we don't just use this weak learner's output as it is. We use this scalar there. We also use a learning rate on top of this. And this is also referred to as shrinkage. So this even further shrinks this value so that we have some type of regularization on the output of these weak learners. And overall, this is how we update our functions with the gradient boosting. So it's nice. We just learned how to apply this gradient boosting idea. And as I said, we can change the loss function to whatever we like. So let's talk about some different loss functions in this section. For regression, we saw that we had this mean squared error, and we also had this mean absolute error. There's also another one called Huber loss, which is a mixture of these two loss functions. So let's talk about this Huber loss because it's something new. Huber loss uses the advantage and the disadvantage of these techniques. The mean squared error kind of has some problematic properties when it comes to large errors, because when the errors or this difference gets really large, as you see, we take the square of that, this usually pulls up all this loss function. So it has a huge effect on that. And in this Huber loss, what we do is that if we have some large value here, we prefer using the mean absolute error. And if it is small value, we can go back to use our mean squared error. So it is a mix of these two squared and mean absolute error loss functions. So it is nice. Overall, visually it looks like this. So this is the absolute mean error. This blue is the mean squared error, and this green is the Huber loss. For classification, we can also talk about some different loss functions. For example, we may have this logistic regression loss here, or we can have this exponential loss here, which uses this exponential, or we can also have this hinge loss here. You can be familiar with this from the perceptrons or SVMs. This logistic regression loss might look slightly different than what you've seen before. This is kind of adjusted for the output, so in this case the output can be plus or minus 1. Similarly, for the exponential, again, this can be plus or minus 1. And for the exponential loss, this usually applies a heavy penalty when the signs are different for y and f xi here. Let's look at this visual here. When we compare the logistic regression and the exponential loss with the step function, we see this kind of behavior here. And as you see, exponential is heavily penalizing the mistakes. So we just learned how to apply gradient boosting, and that allowed us to use some different loss functions. And we also talk about some different loss functions for regression and the classification problems. As a next step, we will see some different implementations of this idea, and we will look at XGBoost, LightGBM, and CatBoost.